Okay. At the end of last video, I introduced that we usually use visible light and infrared EMR as what as energy um, employed by remote sensing systems. And the visible light is relatively easy to address. Usually we use RGB or red, green, and blue, three colors to address a specific, very complex color, actual color when we're looking, when we say in the real world. Okay, um, that's another color theory we're going to talk about later in this semester. But you should know that for any color can be seen by our eyes, we can use a combination of R, G, and B to address it. Okay, but near infrared, not near infrared, let's just say infrared. Infrared EMR is more complex than that. Or you can say the expression or the addressing of infrared is more complex than visible light, because RGB can be used to address a specific color, but infrared, this whole range of infrared can be divided into small subsections, and each one has a specific name. Okay, visible light is from 0.4 to 0.7 micrometers. We're clear about that. But how about infrared? We have near infrared, NIR. It ranges from 0.7 to 1.4 micrometer. And after that, we have SWIR, which is short wavelength infrared. This is the range. And we also have mid wavelength infrared, MWIR. That's the range. And we also have long wave infrared, LWIR. It's from 8 to 15 micrometers. And beyond that, we have microwave. Usually, it's between 1 millimeter to 1 meter. But when you get back to that spectrum figure, you will see that we even have EMR with longer wavelengths, right? Radio wave. And within infrared, the last two categories or last two sections, mid wavelength and long wavelength infrared, they are also called thermal infrared. I will tell you why they're called thermal infrared later. And NIR, SWIR, MWIR, LWIR, they all together, they're also called infrared. Okay, and if you go to different information sources, if you search online, different people, they have different methods to divide infrared into different subsections. And about these boundaries, for example, 1.4 micrometers is the boundary between near infrared and shortwave infrared. 3 micrometers is the boundary between short wavelengths and mid wavelengths. That's only one method to divide infrared. You should not be surprised if other people, they're using different methods to define different sections of infrared, okay? And here I'm going to tell you why MWIR and LWIR, they're called thermal infrared, because we usually consider 3 micrometers, this wavelength, as the boundary between reflected energy and emitted energy. What does it mean? It means that for infrared that has a wavelength smaller or shorter than 3 micrometers, we consider them as the result of reflection, which means that their energy source is sun. Okay, but if you are receiving an energy, infrared energy, that has a wavelength longer than 3 micrometers, it's very likely that this energy is not from the sun, is not from a reflection. It was emitted by an object itself, since that object has temperature, has thermal energy. So usually, if the infrared wavelength is longer than 3 micrometers, we consider that this EMR is what? Is emitted by an object with temperature. It is a form of thermal energy. That's the reason why the infrared radiation who has a wavelength longer than 3 micrometers is called what? Thermal infrared. Okay? Okay, so that's the difference. So you can see here, like I said, the addressing of infrared, the different description of infrared is complex. Visible light, RGB 0.4 to 0.7 micrometer down. Microwave, which we can consider a part of a radio wave, is somewhere between 1 millimeter and 1 meter. Okay, if an EMR has a wavelength longer than 1 meter, we consider that as a pure radio wave. Okay, but you would ask, what about the wavelengths between 15 micrometers and 1 millimeters? Okay, it's very complex. Different people, again, have different ideas, or they have different say arguments about the EMR between infrared and microwave. Okay, but we do not have so much concern about that part, because in remote sensing, especially in passive remote sensing, we care about visible light and infrared. And for active remote sensing, which is not the main character of this class, they are using the passive, the active remote sensing is using microwave as energy. Okay, let's continue. And now let's talk about the collecting of remote sensing data. So you can acquire remotely sensed imagery in an analog format, often referred to as hard copy. It's old-fashioned. Okay, it means that you use a camera to take a picture of the surface of the Earth, and you actually develop a hard copy photo from this camera. So it's called an analog camera. Today, most things, we can say almost everything is digital. So usually today, when we're trying to store data, we usually convert what? An analog photo to a digital photo, or convert analog format to a digital format through the process of digitization. Okay, I'm going to introduce that a little bit, but you should also know that hard copy or analog format is say a method for remote sensing collection. Okay, another method is a popular one. You can acquire remotely sensed imagery in a digital format, such as that obtained by Landsat 7 Enhanced Thematic Mapper Plus, ETM Plus. It's a sensor, a very famous sensor. So digital format is today's, how can I say, the trend, the main character. So today, when you can, you should collect data in a digital format. Okay, but like promised, I'm going to introduce how to, in general, digitalize analog data, analog image. Okay, so here is the concept: image digitization. It is the process of turning a hard copy aerial photograph or other type of remotely sensed analog image into a digital image. Here we have two figures to show the general process of digitization. So here, let me introduce it very generally, okay? So here we have an analog photo on the desk, and you usually use white light to illuminate this photo. And then you use an objective to what? To disperse it, to disperse the white light reflected from the hard copy image onto registered RGB sensors, which means you divide the white light, because the white light is usually considered as a combination of all types of visible light, right? You disperse it into red light, green light, and blue light, and these three types of light, they are, what can I say? They are sensed. They are detected by sensors, and the sensor is going to what? To reconstruct this analog image using digital technology. In other words, the sensor is going to restore the information from this hard copy image in what? In three bands: in red band, in green band, and in blue band. Okay, so when the sensor is scanning the whole hard copy image, the information of this hard copy image will be collected line by line. Okay, so this is the scanning line of the sensor. Okay, okay. And another here is another figure showing you the typical the process of acquiring remote sensing data today, which means that today we usually collect remotely sensed data what? In digital format. Okay, so specifically here, the figure is showing you a satellite platform remote sensing system. So the sensor system is mounted on the satellite. The satellite, of course, is above the atmosphere, looking at a specific area on the surface of the Earth. Okay, so sensor system. Usually today it's digital, but if you are having an analog camera on your sensor system, in your sensor system, there could be onboard analog to digital conversion and calibration system, or tools, or instrument. And then the digital data will be what? Will be delivered to the ground, a satellite station, right? And on the ground, we can do data pre-processing before delivering data sets to our users, okay? Radiometric calibration, geometric calibration, and then there are visual or digital information extraction. For example, we want to do classification to get different land cover types covered by this image, right? And maybe biophysical composition of the area of interest. Okay, of course, in the data pre-processing and data processing process, we need other maybe other ancillary data. What is an ancillary data set? For example, when you are trying to do land cover classification, you may need some reference data to verify if your classification is accurate or is good enough. What's the reference? You need to collect data from the field yourself, or send some people to get field data sets. That's ancillary data, right? And then eventually, when your classification, for example, classification is finished, or your data processing process is finished, you want to distribute your results, or your conclusions to final users. For example, policymakers, right? Policymakers. or all other commercial users. Could be farmers, or could be even people who are working in Wall Street. Okay, today Wall Street is using remote sensing to predict the yield of a lot of crops. For example, soybean. For example, corn. Okay, okay, okay. Now let's talk about different remote sensing data models. But before that, let's talk about remote sensing image. Because no matter what kind of a data model you are using, okay, you are using it to what? To produce image. So image refers to any pictorial representation regardless of what wavelength or remote sensing device has been used to detect and record the EMR. Okay, and we have two types of image. First one is hard copy, photograph, refers specifically to images that have been detected as well as recorded on photographic film. There is actually a hard copy of your image developed on a film. So that's photograph, that's a type of image. But today we usually use digital image, refers to images that have been recorded electronically instead of on a hard copy film as an array of numbers in digital format. Okay, I'm going to show you the structure of a digital image, but you should know a digital image is nothing but a matrix of digital numbers. Here, I'm giving you an example here. So here we're looking at a digital image. Okay, we have a river here in solid black line, right? And other land cover types cannot be accurately differentiated, but I guess this area is mostly covered by vegetation. Okay, let's just accept that assumption first. And let's zoom in a little bit. So here we have a small window open on this digital image, and we look closely at this at this specific small area and zoom in. So we have this small image here. It's a part of this large digital image. You can say there are small units, or you can say there are small squares, and each square is called a pixel. That's a square, right? It's called a pixel. It is the smallest undividable element of a digital image. Okay, and there is always a DN, digital number, assigned to each pixel. And dn is a variable assigned to a pixel, usually in the form of an integer in the range of 0 to 255. So we can say that we have a lot of pixels here. Some of them, they're dark. Some of them, they are bright. And if you compare their DNs, a dark pixel has a smaller value of DN, 32. A bright pixel has a relatively larger DN value, 106, for example. So you can say that DN, if the DN value is large, the pixel is bright. If the DN value is relatively low, it means that the pixel is relatively dark. So DN, you can consider a DN value is the energy reflected by that pixel. If that pixel reflected a lot of energy, its DN value on this image will be large. On the other hand, if a specific pixel reflected a very small amount of energy, at a specific band, then that pixel will be dark. Okay, so this is the idea of pixel of and digital number dn. Okay, let's talk about more about digital image. So here we can say that this image here, no matter this a small image or this large digital image, it's a bunch of what? Of pixels with dn values. So it has what? It has rows, row 1, row 2, row 3, row 4, and etc. It also has columns, column 1, 2, 3, 4, 5, etc., etc. So this is actually a matrix. A matrix is nothing complex. A matrix is a collection of points. Each point has a coordinate, a pair of coordinates to address its position by row and column. And for each point, there is a specific value. Okay, so a digital image is stored in a matrix or array format. Okay, there are rows, there are columns, and for a specific row and a column numbers, we have a specific pixel with a specific value, dn value. Each digital value is located at a specific row and column in this matrix. Dataset consists of n individual multiple spectral bands. What does it mean? It means that for a remote sensor, it is not detecting the whole range of visible light or infrared. A sensor has multiple bands. Each band is responsible for a specific range of EMR. For example, here we have 1, 2, 3, 4, 4 bands for a specific sensor. It means that when the sensor took an image for a specific area on the Earth, it actually took 4 images for the same area, but each image is trying to address the reflecting energy of the area at a specific band. For example, band 1 is for R, is for red. Band 2 is for G, for green. Band 3 is for B, blue. Band 4 is for near infrared. What does it mean? It means that for band 1, for image 1, for the image created by band 1, each value here is a dn value reflecting what? Reflecting the energy, the amount of energy reflected by that pixel. It means that, for example, for pixel 1, 1, the value is 10. This 10 is the energy reflected by that pixel at band 1. Band 1 is for red. This 10 here means the reflected energy of red light. Okay, if you follow this logic, you could expect that for this same pixel at band 2, it should has another dn value who addresses the reflected green energy from that pixel. And similarly, for that same pixel, it has another dn value for blue band who addresses the reflected blue energy, okay, from that pixel, and also for near infrared. So a sensor could have 4 bands like this, could have 40 bands, could have 400 bands. So when we're talking about remote sensing imagery, the first question you should ask, what is the band I'm looking at? Okay, what is the band I'm looking at? Because a sensor could have multiple bands. Even for the same sensor, even for the same area covered by that sensor, detected by that sensor, different bands could have different what? Could have different reflected energy, even for the same pixel. Okay, okay. The concept of band here is pretty important. Okay, let's continue. And except DN, we also have something called BV. It's called brightness value range. Okay, so it decides possible pixel values. It's a quantization level of the sensor systems. What does it mean? You can consider this as the sensitivity of the sensor. Okay, okay. The greater the range of B wave, the more precise the measurement. So usually, for example, here is an example of B wave. So brightness value range, it is often 8 bits, which means that we can use 2 to the power of 8 values to address any value or any tone from black to white. 2 to the power of 8 is 256, right? It means that when the sensor collects energy from the surface, it will give a specific value to that collected energy. If the sensor is 8-bit, it means that the sensor will assign a value to that reflected energy somewhere between 0 and 255. Of course, usually it's 8-bit, which means there are 256 possible values can be used by this sensor. If the sensor is more accurate, it's 10-bit, it means that there are 1024 values can be used by the sensor. If it is 12-bit, there are 4096 possible values can be assigned, can be used by the sensor. But usually 256 is good enough. Okay, for example, at band 1, which is red, a specific pixel did not reflect any red energy, any red light. It means the energy received by the sensor at red band is 0. So okay, I will just give 0 for that pixel at red band, and that pixel at red band is totally black, On the other hand, if a pixel is pretty good, is perfect at reflecting red energy, it reflected all red energy, that pixel will be assigned a value of 255. And for that pixel in the image, it will be pure white. It will be pure white because usually it's convenient to use grayscales to address different levels of energy. So if it is the reflected energy is 0, simply give it black. If the reflected energy is full, which means that all energy was reflected by that pixel at a specific band, then we just assign purely white to that pixel. You will say, okay, because it's red band, I want to use black and pure red to address that. Of course, you can do that, but it's very distracting because you have 4 bands. Of course, you can use RGB for 3 bands, but how about infrared? Infrared has no color to our eye system. Actually, we cannot say that. What color would you assign to near infrared image? So let's just ignore that. Let's just eliminate the difference of different colors. Let's just use grayscale to address the different reflected energy by different pixels, okay? From pure black to pure white, okay? Okay. So in the last part of this video, I want to talk about the digital image data formats. So we know the meaning of different bands from a sensor. We also know how to locate a pixel, right? By its row number and column number. We also know the meaning of the value here. For a specific image, it's called digital number. It's a relative number assigned by you, And what's the foundation? What's the basis of digital value? It's BV. BV is the brightness value detected originally by the sensor. Okay, so BV is from 0 to 255. Of course, you can also assign the same value as digital number in an image, right? That's the easiest way. So your BV range is consistent with your DN range. But of course, you can change DN range from 0 to what? To 1024. You can simply just rescale your BV range and project to the DN range. Okay, so BV is the basis of DN. But how to store images or images on your PC, on your hard drive? There are different formats. Okay, for example, here we have 3 images here. They are from a sensor, band 1 of that sensor, band 2 of that sensor, band 3 of that sensor. So all pixels on the image from band 1, they're assigned A, right? Same value. Okay, let's just assume that. B, pixel B's, they are from band 2. Pixel C's, they are from band 3. So we have 3 basic data storage formats: band interleaved by line, BIL, band interleaved by pixel, BIP, and band sequential, BSQ. What's the difference? Okay, here is the difference. So we have 3 images from 3 bands, right? Pixel A's, pixel B's, pixel C's. They also have their column numbers and row numbers. So if it is BIL, this is how you store the data. So you store the first row of your image, right? So first row of band 1, A. First row of band 2, B. And first row of band 3, C. And then second row of band 1, 5A. Second row of band B, 5Bs. Second row of band C, 5Cs. So you continually do this. So this is how you store data when you are using BIL format. And what is A? What is a B? What is a C? A, B, C, they are specific values for a specific pixel. Okay, could be BV value, original BV value, could be DN value, right? So if you are using BIP format, it's what? It's by pixel. It means I will just store the value of pixel 1 for band 1, which is A, then pixel 1 for band B, which is B. Sorry, for band 2, which is B, right? And I will store the value for pixel 1 for band 3, which is C. What is pixel 1? Pixel with row 1, column 1. So that, okay, now I have finished the storage of pixel 1. Let's jump to pixel 2, which is pixel row 1, column 2. Then pixel row 1, column 3, pixel row 1, column 4. When all pixels in row 1 have been finished, we go to row 2 and repeat this process. That's BIP. BSQ is very straightforward. I store band 1 first, and then I store band 2, then I store band 3. And within each band, the sequence for pixel here is just the sequence of column and row. So for band 1, right, that's the first part of the storage. We have pixel 1, pixel 1, 2, pixel 1, 3, etc., etc. and then pixel row 2, column 1, and then pixel row 2, column 2, and repeat and repeat. When the first image, in other words, the image from band 1 has been finished, we go to band 2. So if you're asking me which one is more popular today, I cannot be sure. I actually cannot be sure. But what's important here is that you know when you are looking at an image on your screen, it's usually been visualized, which means you don't have to worry about the 4 different formats of the data storage. But if you're doing research future in remote sensing, or later you're going to work in this business, sometimes you need to code. You need to know how these digital images are stored on your hard drive. You need to know the actual data structure of different formats for remote sensing images. Okay. And commonly used image formats. Okay, so we have JPEG, TIFF, BMP, right? IMG is the most popular extension or formats in remote sensing. Okay, so here only one slide. You need to know different methods to store remote sensing data, and you need also to know very commonly used image formats or extensions, you can say, on your PC. Okay, so this video is relatively longer because we discussed some very basic but important and also relatively complex concepts here. Okay, see you in the next video.